All right, some questions were asked about some of the bookworks in the first bookwork set that's entitled Reaction Rates and Rate Laws. I wanted to address some of those because some of them concerned some folks and they weren't as clear as perhaps they could have been. In both 15 and 27, the question is about the rate, and so that requires a knowledge of what affects and what does not affect the rate and the rate law. And yes, you can't see my head. Better. Irrelevant. All right, now, so for 15, it asks about the rate constant. For 27, it asks about the rate. In 15, it says if you change the temperature. So here's how you have to look at this. If the rate is equal to some constant times some concentration, all right? If I change the temperature, in most cases, there's a greater chance for collision, therefore the rate will go up. Now, if this does not change and the rate goes up, what must therefore happen to the rate constant? It must also increase. All right? Similarly, if I'm looking at a catalyst, if I have some rate, let's say this is an exothermic reaction, and I say, okay, if I add a catalyst which effectively lowers the activation energy, how frequently or how fast will the rate go? The rate will increase. Why? Because there's an easier pathway. Again, we're not changing the concentration, but the rate increases, therefore K increases. That's all of 15. The first one has no effect because if you up the concentration, that will up the rate, but it won't affect the rate constant. All right? In 27, it asks about concentration A, concentration B, and so forth. C and D, same thing, raising the temperature, lowering the activation energy. If, however, in the case of this one, the rate is strictly for B, and you don't change B, but you change A, then it's not going to have any effect on the rate. If A is not in the rate constant and you change the amount of A, it's irrelevant. It doesn't go any faster, any slower. All right? That's 15 and 27. 31, the question is posed about in an experiment, blah, 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 0.0048 moles is in a 2 liter and consumed each second. I'm going to shift this backwards so it looks a little better. No, okay. Have fun with that. This is the first time using this particular device, so sorry about that. All right, now it tells you that 0.0048 moles are in a 2 liter container, and that's the concentration, and that is the amount being consumed per second. All right, so if you do this math, you get 0.0024 molarity, and that amount of molarity is decreasing per every 1 second. All right, so that is the rate. Now, the question is, how will that affect the rates of the others? This is the big ticket item, all right? So, if this much of the pH 3 is going away per second, how much of this is being made? Okay, this goes back to first year chem. For every one of those, or 4 of those, 1 of those. So if 0.0048 moles of pH 3 is being consumed, then 0.0012 moles of P4 in those 2 liters is being created. Why? Because if you look at the pH 3 rate and look at the P4 rate, you multiply by 1 P4 per every 4 pH 3s, and you can see the rate of consumption. Similarly, this is going to be 4 to 6, so this is going to be what? Brain. 4, same, 6, 48, I don't know. Brain's not working, it's late in the day. 0.0048 times 6 divided by 4 equals 0.0072. Yes, I should have been able to do that in my head. So 0.0072 per 2 liters. All right, straight up stoic, 4 to 1 to 6. So you're going to see questions where they ask about the consumption and the creation, and it again is basic stoichiometry. All right, That's 31. 35, the question is posed, all right, calculate the rate of decomposition. All right, well, how much a rate is simply a concentration per time. So if you know that from 0 to this time period, this much was consumed, then 0.5 molar was consumed in 0.216 times 10 to the 4th seconds. Then it asks about the second time period, and it says specifically from the first time period to the second. So we're going to go, okay, it's 0.5, or we should say it this way, 0.25 minus 0.5 over full 0.36 times 10, whatever, times 10 to the 4th, minus 2.16 times 10 to the 4th. So you're going to get 0.25 over, again, 2.16 times 10 to the 4th. Now notice, is there a difference in the rate? Sure. Whatever this is going to be twice the rate of whatever this is. It's going away twice as fast in the first case as it is in the second. All right, so the rate changes based on the concentration. All right, that's 35. All right, I'm going to bring this to center screen. You can rewind at any time, so I don't need to keep that up there. All right, so in this case, they gave you pretty straightforward. They said, all right, what did I do? I kept this constant. I doubled this. What happened to this? It doubled. Therefore, since this and this increase at the same amount or the same ratio, all right, Cl2, we don't know what these powers are. Double this, double that, first order. All right, this case we held these constant, doubled this. This went up by, looks like 4 times. So this was doubled, and this was 4 times, so second order. Now, if you want to do it in a more detailed fashion, I can show you that with the last problem. All right, so give me a second. Should have had this ready. The last problem is 45. So let's go through that one very briefly. Apologies, should have been more organized. Okay, so we've got the concentration of HB, concentration of CO, and the rate. All right, HB, 2.21, 4.42, 4.42. All right. And this one is 1, 1, and 3. And the rates are 0.619, 1.24, and 3.741. That doesn't look terrible. All right. But if we wanted to do it in a more formalized fashion, we would go something like this. All right. We would go, okay, we're going to take this, we're going to call these set 1, set 2, set 3. I'm going to take, since CO is not changed from set 1 to set 2, I'm going to go, okay, the rate equation is going to be equal to K, concentration HB, concentration CO, to some X and some Y. So I'm going to do number 2 first, since it's a larger value. I'll put it on top since it divides nicely. We're going to have a rate of 1.24 equals K. Can't forget that. The concentration of HB is 4.42 to the X, and the concentration of CO is 1 to the Y. All right, and we're going to put that all over number 1. And that's going to be, the rate is, oops, sorry. Yeah, that's right. Now I'm making a bloody mess. This should be 2.21. No, it shouldn't. 4.42. Sorry, brain fart. All right, so should redo, but I'm not going to. All right, and so number 1 is 0.619 equals K, 2.21. Now I'm back on track. 1 to the Y. All right. So divide that, it's pretty close to 2. K over K is 1. All right, 4.42 to the x, 2.21 to the x. We divide the things inside and we get 2 to the x. If you have trouble with that algebra, see me. And that's 1 to the y over 1 to the y, which is 1. So 2 equals 2 times 1 times 1, 2 to the x, therefore x is 1. All right? Now in this particular case, they held this constant, but let's say they didn't. Now that you've figured out one of them, you can do the other one. So what are you going to do? You're going to take, let's say, the third over the first, doesn't matter which. All right, so let's try that, 3 over 1. So same equation, rate equals 3.71 equals K times what? Concentration HB is 4.42 to the, what do we figure out? We figured out it's to the first. All right, times what? 3 to the y, we don't know. All right, over 2.21 equals K, 4 point, let's do, since we did the first one, let's do the first one. All right, so the rate is 0.69, 619, excuse, time 2.21, trying to talk too fast, to the first, 1 to the y. All right, now, everything in here we know, so, except for y. So let's just do it. It's 3.71 divided by 0.69. Wonder why that wasn't working. Divided by 0.619, slower to go faster, comes out of almost exactly 6. Okay, K over K is 1. 4.42 to the first over 2.21 to the first is 2. And 3 to the y over 1 to the y is 3 to the y. All right, so what do we have? We've got 6 equals 1 times 2 times 3 to the y. So 6 over 2 equals 3 to the y. 3 equals 3 to the y. Therefore, y is also 1. So our rate equation would be K, concentration HB to the 1, concentration of CO to the 1. All right. Now, if I want to go further, I could take and solve, I think it asked you to do this, solve for the rate law and find the rate constant. Okay, so let's take it one step further. The rate equals K concentration HB to the first, concentration CO to the first. Pick a set of data and plug it in. All right? Now, I've neglected the units, but the rate is in millimoles, millimolarity per second, and the concentrations are in millimoles per, or just millimolar, or millimolar. So pick one. So let's say we'll do number 3. 3.71 millimolar per second equals K, we don't know. All right. HB is 4.42 millimolar, just plain old millimolar. And the last one is 3 millimolar. All right, so there's 2 bits we got to do. The first bit we got to do is solve the numbers. And so we take 3.71 divided by 4.42 divided by 3, and the numerical value for K is 0.27978 blah 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 blah. All right, now the other question is, what's the unit? So let's look at that. We've got millimolar per second divided by millimolar times millimolar. If you can't read that, I'm sorry. All right, and so what's that work out to be? One of these millimolars cancel, and so the final answer looks something very oddly like 0.27, let's just say 0.28. 1 over millimolar times seconds. Now you may see it expressed in a book as 0.28 millimolar to the -1, seconds to the -1. And if that throws you off, well, just ask me and I'll give you a hand. All right, so there is a bit of an explanation. Hopefully you can see this. Mash the like and subscribe buttons.